So here we look at the example of how we can implement the modulo 2 summation, which is also called the XOR, and we have the binary bits D of t given as 01001011. This is what we want to transmit. The question is very simple. We are going to be using the XOR truth table. And the XOR truth table says when you have A, B, what is your output? A XOR B. We just list the possible combinations. Our possible combinations of A and B are 0001, 10, and 11. And we normally say that we only give for XOR only a 1 when bit 1 is the input. So we say this is 1 and this is 1. When you have 2 zeros, this becomes 0. When you have 2 ones, still this becomes a 0. So we are just going to be comparing our data and our PN sequence. So for the first PN sequence, 0 XOR 0 is 0. That is what we get here. Again, 0 XOR 1 is 1. When we have 0, our PN sequence will not change. This is the first PN sequence. And then we compare the second one. When we have 1 and 1, our output is 0. 1 and 0 from our XOR table, we know this is going to be a 1. 1 and 0 again a 1. 1 and a 1 is a 0. The operation that we're performing here is simply the XOR operation. And therefore the transmitted pulses are this one. And the only thing we can observe with this pulse is that 0 is represented by a positive going pulse and 1 is represented by a negative going pulse. So when we receive this signal on our receiving end, you'll multiply again with a similar sequence like we have already seen, 0, 1, 1, 0, 1, 0, 0. This is what we had received, 1, 1, 0, 0, 1, 1, etc. This one is the same as this one. So we want to be able to detect what we had sent earlier. So when you multiply this 0, again we are doing the XOR. 0 XOR 0 is 0 again. 1 XOR 1 is still 0. 1 XOR 1 is still 0. 0 XOR 0 is 0. 1 XOR 0 is 1. So the only thing we notice with this model is that, again I repeat, 1 is represented by a negative pulse and 0 is represented by a positive pulse. That is the only confusion that may appear. That is our example of our DSSS encoding that we have. The most important thing is how are we able to generate our encoded code that we are transmitting. When we know our PN code, we are simply doing the XOR operation. Now very quickly we look at the DSS that combines the BPSK modulator. Just this more or less of a summary of what we have already said. We have our information bits that are XORed with our PN sequence using modulo 2 summer or adder. Then we have, once we do that, we pass that signal through a low pass filter, and therefore at this point 1 bit of information that we are setting is represented by n bits from the PN sequence. This results in a wideband baseband signal. We pass this through low pass filter so that we can reduce some of the sharp changes in line code that has been added to the PN code. Once we have received what we referred to as our MT in our previous discussion, we perform now the BPSK modulation. Therefore, we are able to get here our MT cos omega c of t. This is what we transmit to our channel, that is interference limited. In summary, we say that random noise produced by PN code generator. The baseband information is spread by multiplying it with the PN sequence. Each bit in the information data is represented by multiple bits. A single pulse of PN sequence is called a chip, that we have already said before. And then we say that the spreading code spreads the information across a wider frequency band. A 10-chip spreading code, for example, will produce a spread signal that is 10 times bigger in bandwidth. And generally, we say that the combination that we're performing with the spreading code, we use the XOR logic operation. And we have also seen that, in summary, that we perform modulo 2 summation, and we see that the DSS signal is BPSK modulated using frequency carrier to enable transmission over the communication channel. Now you look at the DSS with coherent BPSK demodulator. Look at this diagram. This is something we have already discussed. So what we'll do is very quickly talk about it. So you see that a coherent or differentially coherent binary PSK is used in this receiver. This figure shows that the received DSS signal is first passed through a wideband filter, and the DSS with BPSK demodulator uses a locally generated PN code, and this PN code is multiplied with our U of t, the one that we said that is a combination of MT plus interference I of t. So when we perform this multiplication, we have seen that we are able to get two signals, one with wide band and with a narrow band. And we perform PPSK demodulation, we are able to get our MT. In summary, DSS with coherent BPSK demodulator may be used in the receiver, and the figure we have seen above shows a functional block diagram of that DSS receiver. And as we have seen, the DSSS signal is first passed through a wideband filter, and a DSS with BPSK demodulator, we have seen it using a locally generated identical bit code similar to the one that was used to spread it in a block diagram called correlator. And a DSS correlator is a special matched filter that responds only to signals that are encoded with a PN code that matches its own PN code. So in this instance, when we talk about a matched filter, we are saying that when we match the PN code at the receiver with the one that is similar to the one that was used to transmit, then we consider that as a matched filter, and is the one that we use in our DSSS correlator. And we have seen that this correlator helps to separate the desired coded information from all the other possible signals, including the ones that were sent as interference or jamming signals. And the received DSS signal is first processed through a DSS spreader that is used to spread the signal. And we have seen that the spreader, in actual sense, what it does is to spread the interference, and therefore the effect of the interference becomes minimal, and they are filtered out once we apply our bandpass filter. So in conclusion, the DSS spread signal is then demodulated with a BPSK demodulator, and for proper operation, a synchronization system is used so that the locally generated PN sequence is synchronized with the PN sequence used to spread the signal at the transmitter. And finally, the two PN codes are aligned to within a fraction of the shift rate during the acquisition phase, followed by tracking that applies some concept of phase locked loop technique. So some advantages now of DSSS. One of them is that it offers low probability of interception, and the transmitted energy remains the same, but the wideband DSSS signal looks like noise to any receiver that does not know the signal's code sequence. So there is extremely low probability of intercepting this signal. This we have seen. Signal with this PSD or power spectral density appears to any interceptor as noise, and therefore no one can be able to decode that signal. The other advantage of DSSS is that it offers increased tolerance to interference, because DSS modulators process a narrowband information signal to spread it over much wider bandwidth, and this spreading of the information desensitizes the original narrowband signal to some potential interference to the channel. And again, this we have seen. Now, increased tolerance to multipass is another advantage that is offered by DSSS, in which case, by the virtue that we provide increased tolerance to interference, this also means that there is increased tolerance to multipass interference, and therefore multipass energy may be used to the advantage of improving the system performance. The other advantage that is offered by DSSS is that of increased ranging capability, in which case the timing error is directly proportional to the signal bandwidth, and this property enables DSSS to measure distance or equipment location through a method known as triangulation. It is beyond the scope of this lesson or this course, but we should observe that with the DSSS there is increased range or ranging capability that is offered to the user or to the transmitter.